So Physics Fun, looking at Newton's laws of motion, and today we're going to focus on his second law of motion. Beforehand, let's watch some short videos on Newton's 3 laws of motion.
Welcome to Mimu Math and Science. In this video, I'd like to talk about Newton's 3 laws of motion. Sir Isaac Newton lived in the 1600s and developed 3 laws to describe all states of motion. Law number 1, or also called the law of inertia, states that matter wants to resist any change in motion. If an object is at rest, it wants to stay at rest. If an object is in motion, it wants to stay in motion. Also, the more massive an object, the greater its inertia. These dominoes will stay at rest forever unless an outside force acts on it, like this push from someone's hand. Also, this player punts the ball. Due to inertia, what does the ball want to keep doing? Stay in motion. But why doesn't? Because outside forces like air friction and gravity act on it. Why is this car hard to push? That is because it wants to stay at rest and it has a larger mass than the man trying to push it. Law 2 states that the acceleration of an object depends on the force acting on it and the mass of the object. There's also an equation to go along with this law, and it states that force equals mass multiplied by acceleration. Look at this golf swing. The golf club has a high rate of acceleration and strikes the golf ball with great force. This hammer has a greater mass and acceleration than the piggy bank, and look what happens. And finally, law 3 states that for every action, there's an equal and opposite reaction. Look closely at this jellyfish swimming. As the jellyfish moves its body backward, it actually moves forward because the water exerts a force in the opposite direction, which causes the jellyfish to move forward. Same with the skateboard. The foot is pushing the skateboard backwards, but the skateboard is going forward. That is because the foot and the pavement is exerting a force in the opposite direction, causing it to go forward when pushing backwards. So there we go, Newton's 3 laws of motion.
Law 1, an object at rest tends to stay rest on. An object in motion will stay in motion. Keeps going at the same speed and direction. That means when a ballast takes the bounce, forces act on it. Features of our planets that act in an instant. One is air resistance, is the ball through friction. Gravity acts upon it, falls back to the surface. Force is anything that changes the state of an object to moving. On Earth, the strongest force is gravity. Oh yeah, Sir Isaac Newton, 3 laws of motion. Law 2, an object with more mass takes more force to move. Force equals mass times acceleration, so you must kick the ball harder to have the same conclusion. The 3rd law of motion states for every action, there must be an opposite and equal reaction. So when that ball is kicked, one force will be given. The other force is demolished the opposite direction. Force is anything that changes the state of an object to moving. On Earth, the strongest force is gravity. Oh yeah, Sir Isaac Newton, 3 laws of motion.
what happens when forces are unbalanced. Welcome to Moo Math and Science in Balanced and Unbalanced Forces. Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. But how are balanced and unbalanced forces different? Balanced forces will cause no change in the speed of an object. Balanced forces acting on an object in opposite directions and in equal strength, as shown in the arrows below, do not cause a change in the speed of a moving object. Objects that are not moving will not start moving if acted on by balanced forces. Remember, forces have a magnitude and a direction. Unbalanced forces are not equal, and they cause the motion of an object to change. When two unbalanced forces are exerted in opposite directions, their combined force is equal to the difference between the two forces. The magnitude and direction of the net force affects the resulting motion. This combined force is exerted in the direction of the larger force. Let's take a look at some real-world examples. The forces acting on the red pool balls are balanced. The downward force of gravity is equal to the resistance force of the pool table. When the white ball strikes the red balls, the forces are now unbalanced and they move in the direction of the force. The forces are balanced on the weights. The downward force of gravity is equal to the resistance force of the yellow rack. The weights do not move. The weightlifter exerts an unbalanced force upward, and the weights move in that direction. The forces on the tennis balls are equal. They are not moving. When the tennis balls are struck by an unbalanced force, it causes them to move. The resistance force of the car is balanced with the downward force of gravity. The car jack exerts an unbalanced force on the car upward, and the car moves in that direction. The car is at rest, and all forces are balanced. When the car that is moving strikes the car at rest, then the forces now are unbalanced, and the car moves in the direction of this force. If you'd like to know more about unbalanced or imbalanced forces, this playlist will help.
Okay, so those are Newton's 3 laws of motion. Let's have some practice with that. We're going to look at his second law of motion, which can be summarized with the equation net force equals mass times acceleration. So what does that mean, his second law? His second law states that the acceleration of an object depends on the object's mass and the force being applied to it. Let's have a look at our question here. It's asking us, what is the mass of a bowling ball if it requires a force of 9 newtons to accelerate the ball at a rate of 15 meters per second squared? So in order to do this physics problem, we can use a guess strategy to help us figure this out. So G is going to ask us, well, what's given here in this information? So you want to look at your numbers and units. So I see 9 newtons. I know newtons is the force. So I can say my force is given to me. So I'm going to write force equals 9 newtons. And then my other variable, acceleration. And if I look here at my units, meters per second squared, I know that's acceleration. So my acceleration is also given to me. My acceleration is 15 meters per second squared. Meters per second squared. Okay. Now what's unknown? What do I need to solve for? They're asking us what's the mass of the bowling ball. So what I want to know, my unknown, is my mass. And your mass is always going to have the units of kilograms. Okay, and I need to solve for mass. So what would be my equation that I use to solve for mass? Well, first we're going to use Newton's second law of motion equation. That's net force equals mass times acceleration. Now, of course, this is the formula for net force. We want to know what the mass of the bowling ball is, so we need a formula for mass. So if you make your formula triangle, multiplication always goes across and division is up and down. We want to solve for mass. So let's cover up our mass, the variable we're solving for, and our formula will read force divided by acceleration. So I'm going to come down here now and write my equation for mass. Mass equals force divided by acceleration. So force divided by acceleration. Now, all I need to do is simply substitute my numbers into my equation. So I'm going to rewrite my equation, mass equals, and what was my force? 9 newtons divided by my acceleration, and my acceleration given was 15. So using a calculator, I can divide 9 divided by 15, which equals 0.6. Okay. And I do need a unit, which would be kilograms. Okay, and so I solved my equation right here in the substitution step just now, and our answer is 0.6. So if our answer is 0.6 and we're asked to grid a number, how would we do that? So let's go to a griddable now and grid our answer. So if we wanted to grid 0.6, let me grab my web page. Okay, we're gridding 0.6 kilograms. So here's your decimal point. So your 6 would go here, and you would have to bubble it in completely, very nicely. Okay, and of course you could put a 0 here, although it's not necessary. And you could also put a 0 here in the ones place. So let's talk about net force now. We just used the formula net force equals mass times acceleration, but what is a net force? Your net force is the overall force exerted on an object. It's measured in newtons. If the net force of an object is 0, then the change in motion will not occur. So look down here. If we have a net force 0 newtons, net force 0 newtons, net force 0 newtons, the object is not going to move. The object's going to be balanced and it will be at rest. So when we look at forces, we're always going to subtract the forces if the arrows are pointed towards each other. So here we have a force of 10 newtons to the right and then a force of 10 newtons to the left. Since they're pointed towards each other, we're going to subtract. So 10 subtract 10 would give us 0 newtons of force. Now, if we look over here at this situation, the arrows are pointed away from each other. So we have someone applying a force of 5 newtons to the left and somebody applying 5 newtons to the right. So again, we subtract these forces, 5 subtract 5, 0 newtons of force, the object's at rest. So here in this situation, I need to know my total forces on the left, and then here on the right, you have a force of 8 newtons. So 5 plus 3 would give us 8 newtons here, okay? But again, our arrows are pointed towards each other, so we'd subtract. So 8 subtract 8 would give us 0 newtons of force, and our box would still remain at rest. Okay, so if the arrows are going in the same direction, we add them, okay? All right, now let's look at the net force for an unbalanced force. Now remember, unbalanced forces are going to cause the motion of an object. So net force, again, the overall force exerted on an object. It's measured in newtons. If the net force is greater than 0, then a change in motion will occur. So let's look over here. Remember, we're going to subtract the forces if the arrows are pointed towards each other or pointed away from each other. So here they're pointed towards each other, we're going to subtract. Here they're pointed away, we subtract. When the arrows are in the same direction, we add. So let's look. So if we have 15 newtons of force to the right and then 10 newtons of force to the left, 15 subtract 10 would be 5 newtons of force. So that's greater than 0, so we understand the object's going to move. And it's always going to move in the direction of the greater force. So we would say that the file cabinet is going to move to the right with a force of 5 newtons because it's going to go in the direction of the greater force. 15 is greater than 10. Over here, arrows are pointed away from each other, so we subtract. 20 subtract 10 is 10 newtons of force. 10 is greater than 0, so this object is going to move in the direction of the greater force. 20 is greater than 10, so the box is going to move to the left with a force of 10 newtons. Here we want to add our forces because these arrows are pointed in the same direction. 5 plus 3 is 8 newtons. 8 subtract 5 is going to be 3 newtons of force. 3 is greater than 0, so we do have motion. And this file cabinet is going to move in the direction of the greater force, which is 8. So it's going to move to the left with 3 newtons of force. So we can look at a scenario of an unbalanced force because here our net force is going to be greater than 0. So here we have a side view of a toy train. We have 2 newtons of force being applied to the right and 5 newtons of force being applied to the left. If we wanted to know the net force acting on the train, these arrows are pointed in towards each other, so we're going to subtract 5. Subtract 2 would be 3. So the net force acting on the train is 3 newtons, and the train is going to move in the direction of the greater force. 5 is greater than 2, so our train is going to move 3 newtons of force to the left. Okay, and we could do this backwards. If we know our net force here is 3, we could figure out what forces are on our right and left.